So the question is, since we have this slotted system, right, it is we know that the mobile node and the base station have to be in total time synchronization with each other, right. If different mobile nodes think that this is slot 3, that is slot 3, then they may try to transmit at the same time, creating a collision at the base station. So that is a basic problem, right. How do we solve that problem? How do we ensure that everybody has the same notion of slots in the system? Somebody may be very near the base station, somebody may be very far away from the base station. Still, the notion of slots has to be maintained by all the nodes. So that is the question. How do we do that? How could we do that? Is it making sense what I am saying? The question that if a node is very near the base station, it will, whatever it transmits will reach the base station very quickly. If the node is far away, we have, let's say 35 kilometers is the maximum range. So by the time it transmits in slot 3 and the signal reaches the base station, it may be slot 3.5. So its data may be spread over slot 3.5 to 4.5 instead of slot 3 to slot 4, right? How do we solve the problem? So the basic solution here is that what is important is not for everybody to have the same idea of time, but everybody to send information so that it reaches the base station at the correct instant of time. Okay, that's the key idea here. So basically it means that if you are expecting me to transmit in slot 3 and I know that I am, let's say, 1 millisecond propagation delay away from you, I should transmit 1 millisecond earlier so that I reach you at slot 3, because the base station is the important thing here. So as long as the notion of time at base station is maintained by everyone, things will be fine in the system, right? So the question is how to compute this time. Okay, how do I compute? So first thing is how do I do the transmission, and the second question is how do I compute. Okay, so see what is happening here. So let's say this is the node in which you are transmitting, this is the slot in which you are transmitting. So first of all, there is a one-way propagation delay that happens. So this is the one-way propagation delay, this is what reaches the mobile node, correct? Once this reaches the mobile node, what does the mobile node know? It knows that my transmit slot is +3. So it knows that I should transmit in this slot. Okay, so it transmits in slot 4, which is actually being transmitted here. Okay, so this is what the mobile node is sending here. Okay, and that is further pushed by another propagation delay, and this is when it gets received at the base station. Okay, is it making sense? So instead of sending it here, basically all that it means is there is a two-way propagation delay involved. There is a one-way propagation delay for that, and there is a one-way propagation delay for what I am sending from the mobile node to the base station, correct? So there is a two-way propagation delay that is involved. So what do I need to do in order to transmit, in order to reach the base station when the base station understands it as slot 4? I have to transmit it in advance, right? So basically I have to advance it by this two-way transmission delay, right? I have to send it, so instead of sending it here, which is where I would have originally sent, now I have to send it at this point. So this being the two-way transmission delay. So I send it in two-way transmission delay in advance so that it reaches the base station exactly when the base station expects it. Okay, so that is basically the idea. So there is a one-way transmission delay in this direction. I know that there will be another one-way transmission delay in the other direction. So anything that I want to transmit to the base station, I transmit it a two-way transmission delay period earlier, right? So that's all that is there to this notion of timing advance. Okay, so basically that's what the time synchronization channel is for. So the time synchronization channel, what happens is, let's say this is my notion of the time synchronization channel, TCH. Okay, time synchronization channel. So what happens here, let us say this is the base station. Okay, so what the base station is doing is it's transmitting a waveform in this time synchronization channel. Okay. Now this has a propagation delay before it reaches the mobile node. So let us say it reaches the mobile node here at this point. Okay. This is how the waveform is going to reach the mobile node, correct? So what the mobile node does, so there is, let us say, a pattern. So the mobile node starts receiving the time synchronization information. Let us say, to make it easier, let us think of it as bits instead of as this pulse. Okay. So let us say my time synchronization bits is 1010101. Okay, fine. Let us say I am going to transmit these bits. So when the base station starts transmitting, it knows what is the time it started transmitting the bits, correct? So the mobile is going to receive the bits. Okay, this is just like a training sequence. Okay, instead of I could even transmit the training sequence. It doesn't matter what sequence I am transmitting. Maybe even the training sequence I transmit. Okay, so the mobile is going to start receiving it at some point. Okay, and as soon as it finishes receiving, okay, it transmits it back to the base station. So let us say this training sequence is x. X is the duration of your training sequence. Okay. So what does the base station know? Base station knows that the duration of the training sequence is x, so it should be kind of t0 plus x. Okay. When would the base station have finished transmitting the training sequence? T0 plus x, right? So but now it knows that it has received it at time t1, where t1 is equal to t0 plus delta plus x plus delta, correct? Right? So now what does it know? What is the timing advance? Okay. So it knows that I have received it here. It knows that I should have received, if this mobile node was standing right next to me, then I would have received the signal here at this point, right? I would have started receiving the signal here. Is that making sense? Okay. If there were zero propagation delay, the base station knows that I would have started receiving the training sequence back at t0 plus x, because x is the amount of time it takes for that thing to get transmitted. Okay, so I would have started receiving the first bit here, and I would have finished receiving it at t0 plus 2x. Correct? So now it knows that here is where I expect to hear this guy, here is where I have heard this node. Correct? So this minus this is the timing advance. Okay, it's as straightforward as that. So it knows that delta is equal to t1 minus t0 plus x. Okay, so even though I don't know this delta, okay, so I don't know the value of the propagation delay, I know what is the timing advance that I should use, okay, by just making the measurement at the base station. Okay. So what it does is, then it conveys this delta value to the mobile node in the timing synchronization channel. Okay, so in the timing synchronization channel, it will convey the delta value to the mobile node, saying that advance your notion of time by so many microseconds. Okay, so there is no, it doesn't need to know what is the exact propagation delay, etc., etc. Those measurements are not so important. It just sends a sequence of bits. It waits to see when the responses come. This minus that, it knows when it should have come, and it knows when the actual responses come. This minus that, it knows advance your notion of time by so much units of time. Finished. Okay. So that is the basic idea behind timing advance. So if you look into the details of GSM, they will mention that every 24th slot is reserved for time synchronization. Okay. Every 24th slot in a logical channel, not in a physical channel. Okay. Okay. So here we see that the uplink and the downlink are shifted in time by 3 slots, correct? So the same slot we were talking, right? If I receive in this slot, then this is the corresponding uplink slot. So why this 3 time slot delay sorry, is because one, we want to keep some time for the timing advance. Suppose if it were the next slot, what would happen? Suppose we had decided, okay, the question is, suppose we had decided that frequency x time slot 1 is downlink and the immediate next slot is the corresponding uplink. Suppose we had decided like that, what would happen? Two things will happen. See, one is your cost of your equipment will go up. Why? Transmitter receiver switching, turnaround. Okay. So basically what you want to do is, the mobile is in the receive mode, it has to finish receiving and it has to switch into the transmit mode in order to send. Otherwise what you have to do is, you have to build both a transmitter and a receiver into your handset. Right now you are doing with a single transceiver which performs both the functions of receiving as well as transmitting. But in order for the transmitter and receiver to switch between the two functions, you need some time. Okay. So that is one time that you need, and the second is, you need to give some time in order to take into account this timing advance. Okay. So both of these together bring it to 3 slots. Suppose it were 2 slots, then what will happen? Let us say the transmitter receiver time can be ignored. Okay. Only the timing advance is there. Suppose it were 2 slots, what will happen? Okay, the timing advance will be maximum 1 time slot, which will have an impact on distance. How? How will it have an impact on distance? Correct. You cannot accommodate a mobile node which is far away, because by the time it sends its timing advance information, you know that you are going to be out of that time slot. Correct? So the maximum distance, so why is GSM 35 kilometers? This is the reason. Okay. The timing advance is the reason. How many bits have you allocated in order to convey the timing advance information? That determines what is the range, right? Otherwise it's just determined by power. The more I scream, the farther I can be heard. Correct? But otherwise, in a slotted system, I need to take into account the timing advance. So if my timing advance is able to accommodate only 3 slots, okay, timing advance plus the receiver transmitter turnaround should fit into 3 slots. That's why I can go only up to 35 kilometers. If I had made it 4 slots, then I could have gone farther. So if I do that, then there is going to be more delay between 2 subsequent frames. If I push it beyond the if I push it to 4 slots. Okay. So that is why it's kept as 3 slots. Okay. So look at what will happen otherwise to, let's say, slot number 5. If you take larger numbers, what will happen is it will overflow, it will eat into the next frame. Okay. So 3, that's why is, see, it could have been 2. 2 is not a unreasonable number for the spread between the uplink and the downlink. Okay. 2 is also feasible because it would have time for doing the receiver transmitter turnaround as well as to do the timing advance. But if we do 2, then the range will come down, right? If we do 4, then the delay will increase. Okay. So that's why it is 3. Somebody else asked me a question in the break saying that now that we are addressing all the whys, why is there this 20 megahertz separation between the uplink and the downlink? 915 to 935, right? So why is it this 20 megahertz separation between the end of the uplink and the start of the downlink? Okay, 45 is from here to here. Okay, there is no technical reason for why it should be 20 megahertz. There is a lot of such things in technology for which there is no really sound reason. You know, take ATM for that matter. No? Why 63 bits cell in ATM? So some people were saying 48, some other people were saying 75, so they did a compromise and arrived at 63. Okay, so there are many reasons like that also which happen. So this 20 megahertz separation is because of that. You need a reasonable separation between the downlink and the uplink. Okay. If it is too close, you know that it cannot be too close, right? What will happen if it is too close? Interference will happen because the downlink transmitter is more powerful. My downlink is the base station, so the downlink transmitter is more powerful. So the interference will happen if it comes close. Okay, if it goes farther, what will happen? I am taking a larger chunk of the band, right? So I have to find some intermediate. There really is no reason why 20 is a good number. Okay, just regulations. People just decided that we'll have 20. So this is what happens in your timing advance. Okay, so a 6-bit number is used to convey. See, basically that big delta which we saw, right? This big delta is conveyed by the BS to the mobile node as timing advance, right? Advance your notion of time by this big delta number of units. Okay, so in order to convey that delta, you are using a 6-bit number. Okay, so 63-bit time period turns out to be 233 microseconds RTT, which comes out to approximately 35 kilometers. Okay. All right. Any other questions on GSM? So let me try to give a summary here. Okay. We have a bunch of logical channels, physical channels, various types of mapping and all that. Okay. So let me elaborate on VLR by doing this. Okay. So let's try to frame a question here. Suppose your mobile is registered in Mumbai and you are currently in Delhi. What happens when your friend in Mumbai calls you? How does the call get established? By what happens, I mean, is how does the call get established? What will be the steps? Your friend is using a PSTN line. Chalo, I'll simplify life. Okay, so what will happen is, so you'll say PSTN. Okay, it will go to MSC, it will go to the GMSC of Mumbai, correct? Then what will happen? Okay, GMSC will check the HLR. Okay, what does the HLR contain? Okay, it's the home location register, that's fine, but it will say that this is the mobile number. Okay, and it will say currently in which BSC is not in any of the BSCs in Mumbai, right? So what will it do? HLR 1, let me call it HLR 1. It will go to HLR 1. It will say, okay, this mobile number is currently in which MSC? I can't say which MSC, right? Because I am in Delhi, right? So what would have happened is, when I have switched the mobile on in Delhi, I would have registered in this HLR saying that currently in Delhi, okay, under MSC 2. Okay. Is that making sense? In Delhi, again there will be multiple MSCs, but it will say that I am currently in Delhi. When I go to Delhi, I am going to register. As soon as I power on, what's going to happen? All these actions will happen, and as part of the information exchange, I am also going to authenticate my roaming capabilities. Correct? So what is the authentication of the roaming capability? That network is going to call up my home network, find out whether I pay for roaming services or not, and if so, the HLR entry is updated. Okay. So this HLR is simply pointing to saying currently in Delhi under MSC 2. Correct? Now, then what happens? This guy goes back to GMSC. GMSC contacts MSC 2. Then how do I know where I am in MSC 2? MSC 2 is again a large area. MSC 2 is again controlling a large area. correct? So MSC2 is going to look up which VLR? VLR2. Okay, let me say HLR Mumbai and VLR Delhi. Okay, it's going to look up the VLR in Delhi to find out which is the BSC to contact. Okay. Now can you guess why I need two different things, HLR and VLR? Both have more or less identical information. Okay, both are basically going to say that this is the mobile node, this is the current location. That is the key information which is there in both these databases. But why do I need two of them? No, I could, roaming charges are different. Let's leave out the billing aspect. Basically it is for reducing the traffic to HLR. See, if you look at it even from a technical perspective, this guy, the mobile node is in Delhi, right? So from Delhi, if I am going to keep updating the HLR which is sitting in Mumbai, okay, so I am making calls all the time, right? So there is a lot of traffic that is going to be coming from Delhi to Mumbai just to keep track of my location, right? It is the same location update problem which is now expanded to one more scale, right? So I don't want to keep sending information from Delhi to Mumbai saying that okay, I am in this area, I am in that area, I am in that area, right? So instead of that, all that I say is, in Delhi I am currently under this MSC. This is the MSC which is governing my movement in Delhi. Okay. So under that MSC again I will have a lot of VLRs, correct? So that's why. So the MSC2 in Delhi may have a VLR, a lot of cells. Under the MSC I will have a lot of cells, and that is the VLR which is going to record that information. Okay? So VLR basically stands for Visitor Location Register. So every time I am moving within Delhi, what do I update? Okay. Okay, this is the local updates. So the VLR is the one which carries your local location updates. Within Delhi, this is your location that is captured by VLR. Now suppose in Delhi itself you move from this MSC's area to another MSC's area, then you will again update the HLR. See, any global update which you have to make, that you do in the HLR. Okay, maybe that's a good way of trying to understand this. Okay, HLR is basically global updates. So at the MSC level, it basically says I am under this MSC. MSC ID will be stored there. If it is in the home network, then I can store BSC ID also. But if I am in a foreign network, it does not make sense for me to keep updating the BSC ID in a HLR which is in another city, right? So that's why you can think of the VLR as a local HLR. Alright. So what happens when you call your friend? How does the call get routed? Okay, so the second question is, what happens when you call a friend? Okay, so let's see. I have mobile node 1 which wants to call a friend in the home network. So it will go through MSC of Delhi, right, which will go to gateway MSC of Delhi, which will go to the gateway MSC of Mumbai, right? Then HLR of Mumbai. What is it looking up in the HLR of Mumbai? The location of your friend, right? So now if your friend is in Mumbai, your job is easy. If your friend is in Hyderabad, then again it has to go to the gateway of Hyderabad. Okay, so that's what is happening here. So it comes to the HLR of Mumbai, and then this guy says which is the new MSC to talk to. Okay, so this is again a step. This step may have to actually happen twice, depending upon whether this guy is in the same home network or not. Okay. What happens when you are calling your friend who is in the visitor network? It's much easier, right? So you are calling your friend, this guy looks up the HLR. So if you are calling somebody who is in the visitor network, then you just, the call goes up to the MSC, the MSC looks up the HLR and it's able to call back to the other node. Okay, is that making sense? Okay. So of course now the third case to examine is that there are two of you who went from Mumbai to there and you are making a call. Okay, what will happen? If both are visitors, VLR will come into the picture, right? Okay, that's the third case, interesting case, where both are from Mumbai and currently in Delhi. Okay, how does it work this time? So I'll go up to the HLR straight away, right? MS1, MSC Delhi, gateway MSC of Mumbai to look up HLR Mumbai, right? And then this guy will contact back to MSC of Delhi. This guy will look up VLR, and then this guy will call MS2. Right? Yeah, I have left out all the obvious steps, but the main steps are like this. The first node, first mobile node, the first time you will go all the way to the HLR to find out what is your friend's location, right? Since I am making the call, first thing that will happen is it will just get routed through the MSC to the home network. So just depending upon the number, so it will go to the gateway MSC. The gateway MSC will look at the number, figure out which is the home network, whether it is Mumbai, whether it is Hyderabad, whether it is Bangalore, it doesn't matter. It will contact the appropriate gateway in that city, and that's where the HLR lookup will happen. Now once the HLR lookup has happened, then the HLR will redirect it to the current city, whichever is the current location of the MSC. So after that redirection happens, that is when the VLR lookup will happen. So VLR lookup is generally for the incoming part. Okay, you update the VLR when you are in a roaming area. Okay, you look up the VLR for incoming calls. Okay, you never look up the VLR for outgoing calls. Okay, are there any synchronization issues when two gateway MSCs are talking, and when gateway MSC in Delhi does not reach gateway MSC in Mumbai, what will happen? Call will drop. Okay, so yes, there are lots of issues. So these are all called interfaces. In GSM you will find that there are no interface, some other interface. These are all defined as interfaces in GSM. So the interface definition will tell you that this part of it should be completed within so many milliseconds. Okay, if it does not complete within that many milliseconds, the radio resource will be released and you will get some network busy or unreachable or some random error message you will get. Okay, all right. Okay, so that's the basic idea of GSM. Now let's go on to talk about the next enhancement. Okay, so now the question is the natural extension of going on from GSM. So the thing is, I want to carry data in this system. Okay, so earlier I was carrying voice, everything was fine, everybody was happy. Okay. Then it turned out that people invented this thing called WAP, right? You heard of WAP, no? So WAP was invented saying that okay, you can check your email through your phone. So then it turned out that this WAP is very slow, correct? WAP on a GSM network is extremely slow because GSM data rate is 9.6 kbps, right? So data rate is very slow, so you can't send a lot of data on the network. So now if you want to carry data, what is the key difference between data and voice? One difference, if you have to ask, exam question, you can put it in your exams. So data is bursty in nature, while voice is continuous in nature, right? So how does that impact our system design? So I have to go from circuit switching to packet switching. What does that mean? So instead of having continuous allocation or periodic allocation of slots, I want to move the same system to a on-demand allocation of slots, right? So instead of saying that okay, call starts now, even this was a problem which happened in around 99 or so with the first generation of WAP phones, right? So although no data is being transmitted, you are getting billed for the call duration, right? So your call is connected for however long you are connected, that is the duration for which you will get billed in a GSM system. It doesn't matter whether you are speaking or not speaking, right? Till you disconnect the call, that is the call duration for which you are going to get billed, right? Now that doesn't work for data, because if there is the data transmission is very slow, or if the server is not responding, you don't want to pay for the call duration. So the key requirement here was that I should pay for on-demand services. Okay. So I should get slots only when I want them, not at the beginning of the call and keep getting them periodically till the end of the call, right? How do you move the system now? GSM is there, huge amounts of GSM deployments have happened. Now this requirement comes saying that we want to move it to such a system. How do we do that? Yeah, we need to do patches, we need hardware patches and software patches, right? So that is the first thing that we need to understand. So GPRS, basically radio resources are allocated only for a few packets at a time. So GPRS, when you make a voice call, okay, when you make a voice call in a GPRS system, it will work like normal GSM, okay, because you get a periodic slot allocation. You don't want to go into all this overhead of allocation of on-demand packets and all that, right? This is only for data. So the radio resources are allocated only for a few packets of time. So it has all these features of volume-based charging, carrying SMS in data channels, and so on. Okay. So how will you set that up? That is the question. What are the changes that you need to do in order to set up a GPRS network? Okay, so this is how it looks. It looks pretty much the same as GSM. Okay, the same number of boxes are there, the same number of red lines which meaningless notation is there. But what is the change in these boxes? So let's take this BTS box and the MS box. Is there any change required in the mobile node in order to go from GSM to GPRS? Yes, right? What is the change? It has to understand the GPRS protocol, right? In the GSM protocol, all that it has to understand is, if I am allocated frequency channel X, traffic time slot Y as my traffic channel, every time I just have to move 3 slots, I have to transmit. That is the GSM protocol, right? GPRS, now it has to understand that if I have so much packets queued up, then I have to make a request, right, for more slots to be allocated. So I have to figure out mechanisms for slot allocation, and I have to have mechanisms for sending the information. Okay. So the mobile node has to change. Does the BTS have to change? Yes, because mobile node and the BTS are the ones which are executing the protocol, correct? How does the base station notify to the mobile who transmits when? Let's say there are 10 mobiles, okay, each of whom has a huge amount of data which they want to send to the base station. Okay. How does the base station? So the base station has a scheduler which decides the schedule. Okay. Once it has decided the schedule, how does it notify the schedule to the mobile node? So the base station has a scheduler which decides the schedule. Okay. Once it has decided the schedule, how does it notify the schedule to the mobile node? How can I do it? Yes, one way is to send the entire schedule out on the access grant channel, right? Is there an easier way? See, I don't want to use too much of my resources in order to transmit control information. That is the key thing that we have to remember. If I use my access grant channel to send the schedule, I am kind of wasting resources. Not everybody needs to know the schedule, right? Suppose I am the base station and you are the mobile. Okay, each of you have sent me your requests. How did you send me the request? You either asked for a channel on which to transmit the request, or you piggybacked the request along with some ongoing data transmission. Okay, so I got all the requests. Now I have come up with a schedule that, okay, you go first, you go second, you go third, whatever, right? So I don't need to, the schedule is a fairly long thing. I don't need to send the entire schedule to everybody. So what this flag basically says, so similarly you will have slot 1, slot 2, and so on. Okay. So downlink, I am just going on transmitting. All that I say as this flag is which mobile should use the corresponding uplink. Okay. Are you understanding? So what I am saying here is, on frequency channel X slot 1, whatever is the downlink data that I am sending, at the end of that data I will just add one identifier, which is a mobile node's ID. Okay. What does that mean? That means on the corresponding uplink, that mobile will transmit the data. Okay, it's as straightforward as that. I don't need to transmit an entire schedule, I don't need to give a specific access grant, and none of those mechanisms are required. At the end of the data, I just say who is the guy who can use this slot in the corresponding uplink. Which is the corresponding uplink? 3 slots later. You know that the same frequency number 3 slots later is the corresponding uplink. So I just keep on putting whose ID it is. Everybody is receiving the information, right? It's a broadcast medium. See, that is where sometimes you have to utilize the power of the broadcast medium. It's not a one-to-one medium. Although the packet, so this data may be meant for somebody, this information is meant for everybody. It is just an interpretation of the framing, the same normal burst. Okay, you are just saying that I am going to interpret the frame differently now. So if it is a voice call, then I interpret that normal burst as 57 data bits, 26 training bits, 57 data bits. If it is a GPRS data sequence, I have a header, I have information, I have a trailer. In the trailer, I will put this information saying that who is the guy who can transmit in the corresponding uplink. Okay. In case you don't have anything on the downlink, you just send an access grant. That is not a problem, right? When the system is free, there are no issues. You can take any amount of time to talk to each other and figure out things. It's only when 100 people are trying to talk to you, you have to come up with efficient mechanisms. Correct? So what is the key difference now between GSM and GPRS allocation? See, the moment you move to a mechanism like this, where you say that I am just at the end of each downlink frame, I am going to say who can use the corresponding uplink, you are doing 2 things. What 2 things? You are allowing the same mobile to transmit in multiple slots, right? Nothing prevents me, let's say this USF flag is let's say it is MS1, okay? Nothing prevents me from putting MS1 here again, okay? Nothing prevents me from allocating all the 8 slots to the same mobile node, because I just have to put its ID and it can transmit in that slot. In the same way, nothing prevents me from allocating different frequencies also to the same mobile node. Okay. So now all that you are seeing is, okay, it's sort of like this. This is your resource, right? F1 to Fn are your resources, the various frequencies, and you have S1 to S8 as your slots, right? So all that you are saying is who transmits in which slot, okay? So how many in GSM, how many slots could I get? 1, right? In GSM I can get only 1 slot. If I get this slot, then I can get it only in the next block, okay? In GPRS, how many can I get? Any number I can get theoretically, okay? This is not practical, this is theoretical. Theoretically, I can get this. Nothing prevents me from getting this, because all that the base station has to do is to put my ID in that one, okay? I can get this, I can get this, I could get this also, right? I could get any of these slot allocation. So this is my entire radio resource for the uplink, right? So out of this entire uplink radio resource, I could allocate totally flexible number of slots to the mobile on demand. So if I have a huge demand and there is no other user in the system, then I can allocate everything to you. Okay, what happens in practice? In practice, you draw a line somewhere, okay, depending upon the operator. You will draw a line somewhere and say that okay, this much is for pure GSM. Okay, I don't want to mess around with my voice call. I am not going to do any of these fancy allocation for the voice call. So somewhere the operator will draw a line in this resource saying that this much I am going to use in pure GSM mode, and only the remaining I am going to use in GPRS mode. Okay. So even in GPRS mode, so what you have is multiple slots per frame as well as across channels. Okay. So even in the GPRS mode, operators will play it safe. There are different ways of handling this. They are called different levels. For example, look at it like this. Suppose I am allocating 3 slots contiguously to the same mobile. The mobile has to be able to transmit, it has to be able to process so fast. Okay. So depending upon the grade of the mobile and all that, different levels of GPRS exist. So these are called GPRS quality of service levels. Okay. We won't go into the details of that. But the QoS levels in GPRS, the main idea there is they deal with how this multi-slot allocation is handled in practice. Okay. In theory, it is totally flexible. Okay. So that's how you get that number saying that GPRS can carry 115 kilobits per second, while GSM can carry only 9.6 kilobits per second. That's because one of these things is just 9.6 kbps. GPRS, the maximum you could allocate all of it, okay, which is 125 into 8 kind of a thing, right, in theory. Does that make sense? So that's why GPRS can carry more traffic than GSM, although it uses the same FTDMA system. So GPRS requires addition of new class of nodes called GPRS support nodes. Okay. BSC requires something called a packet control unit, and various other elements require upgrades. Okay. All the GSMs are connected via an IP backbone. Fine. So let's go to something interesting in this. So all this is basically data. Okay. What the GGSN contains, what the SGSN contains, and all. So at 5 in the evening, if I make you go through this, it's not going to be very interesting. So let's go to something interesting. Okay. So now, given that I am a GPRS node, what is the key function of a GPRS network? It has to be able to connect to an IP network, right? So through my GPRS phone, I can access my email, which is on an IP network, correct? Okay, look at this figure. Okay, this is a figure. Ignore all these dotted lines. Let's say the mobile node is here, okay, and it wants to talk to this host which is here. Okay, who's going to assign the IP address? See, the important thing is, as far as under this GGSN, all that comes under this GGSN is the same GPRS network. Okay, right? Because it's the same GPRS network, as far as the IP network is concerned, this is just one hop. Okay. So this guy will assign the IP address. GGSN is the one which will assign the IP address to this mobile node. When? So again here there are questions of, do I give it a fixed IP address? Do I give it a dynamic IP address? Right. So by now we have understood, even in wired networks, through our dialing up from home, etc., that dynamic IP address works better than giving fixed IP address allocation. So this guy is going to assign an IP address to this mobile node. Okay. In the GPRS terminology, this is called PDP context. Okay. So it's written there in one of those slides, you will find it mentioned. Okay. So PDP context stands for, what does PDP stand for? Packet data, protocol data packet. Okay. Context basically says the IP address, the assignment. Okay. So in some way, you can think of this GGSN as performing the functions of a proxy server. Okay. So if you look at it from a purely IP network perspective, the GGSN's functionality is very similar to what a proxy server's functionality is. Okay. What is this proxy server's functionality? Let's say IIT, we have a proxy server. Now what happens? I connect from my network. I have a private IP address on my machine. It translates my private IP address to a public IP address so that I can send a request to Google. When the response comes back, it translates the response. It has to keep the mapping of saying that okay, I sent this request on behalf of such and such IP address, such and such port number, right? It translates the response back onto my local network, right? So that is the same function which the GGSN is kind of performing in a GPRS network. Okay. So when the mobile node wants to make a data transfer, what does it do? It initiates the data transfer. The request goes through the wireless part of the network to the GGSN. The GGSN will allocate a IP address to it. Okay, don't look at the dotted lines in this figure. Right? Then what happens? The mobile node now wants to send a packet to the fixed host. Okay, how does it send it? Yeah, it sends it through the SGSN, but it's just a normal IP packet. As far as the node now is concerned, it doesn't matter what network is it. Is it a LAN or is it a GPRS network? It doesn't matter. The function is going to be the same. The same way it constructs a packet on a LAN, the same way you construct a packet, send it on the GPRS network, right? How does it go across the network? What we saw just previously. I do the multiple slot allocation. The mobile node will see how much data is there. It will send the appropriate request to the base station. The base station is going to allocate that many number of slots. Multiple slot allocation will happen. The packet will cross the wireless hop and it will go into the wired network, and from there it will get routed to the end host. Reply will also come back in the same way. Correct? Okay. So now another interesting question is what happens when I am roaming at this point. Okay, when I am roaming from, let's say, this network to this network. Okay, so that's what has happened here in this figure. The mobile node was initially in this network, right? So the mobile node from network 2 is visiting network 1. Okay. So what happens here? When the mobile node is visiting from network 2 to network 1, what changes? IP address has to change. Some notion of IP address has to change. It's like my taking my desktop out of this building, taking it to some other building and plugging it into their subnet. Correct? So totally two different subnets. So something is got to change in order for the communication to continue to function, right? So what will change? So what is the original IP address which this mobile will have? It will have the IP address of this GGSM, correct? So because it belonged to this network, it was originally connected from here. So it got an IP address through this GGSM and it started talking to this host. Okay. So now from here it moved onto this network. What is the first thing that will happen? So the first thing that has to happen is that the GGSN of the old one has to be informed that I am now in the new network. What's happening here? This node has moved from here to here, right? Whom do I talk to as soon as I come into the new network? Who is the first guy I talk to? This BTS, this BSC, this SGSN. Okay. The moment I hit an SGSN, SGSN is equivalent to an MSC. Okay. So the moment I hit this MSC, this guy can help me. Okay. None of these guys can help me because they don't do any IP address assignment, nothing. Okay. So this MSC, I can notify this MSC that, hey, look, I am coming from this network. This was my IP address in that network, and I have an ongoing data transfer. The moment I inform this MSC that I have an ongoing data transfer, this guy can route to the other GGSN saying that such and such node which was there in your network has now arrived to my network. So two things can happen. In one case, the data transfer can simply go like this, okay, both ways. There's no problem. It will work. So you continue to have your old IP address. This SGSN will take care of all the mapping issues. It will forward it to the correct GGSN. So as far as this GGSN is concerned, it doesn't matter whether the data packet came from here or whether the data packet came from there. Okay. So it will just continue to function along this mechanism. Okay. That is one possibility. The other possibility now is, now if these are far apart, then what you want to do is you want to take a shortcut, right? So at that point this SGSN will also contact the GGSN of the new network, get a temporary IP address for this network, and then maintain the mapping. Okay. See, again there is a lot of history. CDMA doesn't have to deal with so much of historical baggage, right? So now even in this, if you get a free slate design, you can always do something very efficient, very effective, all those things are possible. Now this design has happened keeping in mind that there are millions of dollars of GSM equipment which have been deployed. Okay, there are already millions of subscribers. Given all that, so under those constraints you have to come up with a design with minimum additional cost. You have to move from circuit switching to packet switching. So that is why this is beautiful. Okay, if you forget, if you throw away GSM, you throw away GPRS, you can do something like WiMAX, which is something totally which is very similar to GPRS in functionality, but which is able to do a clean slate design, right? Okay, so if you look at the GPRS stack, so the MA at the application layer, you are talking from the mobile node to the GGSN, right? So that is a conversation that's happening at the application level, but it has to come down the stack here, go to the PHY, and then it has to cross this, and then it has to come up, go down, and so on. Okay, so that is the actual physical path which your data is going to take, right? So what happens in GPRS is it has two additional layers. One is a LLC layer, logical link control, okay, and another is called the RLC layer, okay, radio link control. Okay, so the radio link control actually deals with packets at this level, while the logical link control deals with packets at this level. Okay. So what this means is, at this level the radio link control has layer does the retransmission. So I have a big packet that comes from here. Let's say this is the application packet that I need to send, right? At this level it's broken up into small packets at the logical link control, right? Each of the LLC packets may again be broken up into further smaller RLC packets. These packets are transmitted, and here there is a ARQ mechanism is in place. Again here at the LLC level, where I need to make sure that the whole entire packet has been received. Okay, so here I am going to receive the small packet. At the small packet level I have ARQ. Again at the LLC at the large packet level I have ARQ. Okay, so here also I have an ARQ mechanism in order to handle packet data. So ARQ mechanisms for packet data is basically a retransmission mechanism. ARQ mechanism for packet data, there are two mechanisms. One is at the RLC layer and the other is at the LLC layer. Okay. What is the ARQ mechanism to be used? There are two different layers, right? Stop and wait, selective retransmit, go back and which one? So at the RLC layer I am going to say stop and wait, right? At the LLC layer I am going to say selective retransmit. At the LLC layer, if you have got one packet which has come through, you don't want to do any go back in, right? You just want to say send me that one packet which I didn't get. So that's why you are doing selective retransmit at the LLC layer. Okay. How does GPRS carry SMS in data channels? Okay, actually that is it's quite what do you say not very relevant these days. I mean, it was very relevant up to about few years ago. So GSM, what happens is GSM carries SMS in signaling channels. Okay, what are the signaling channels? The dedicated control channel, the associated control channel, those are your signaling channels, right? So in GPRS, since it knows how to handle data, GSM was forced to do that because it didn't know how to piggyback it on the voice channel basically, that's all. So GPRS knows how to handle data, so it just carries it as part of the normal data itself. Okay. See, GSM sometimes you may find that because if there are too many SMSs in a system, it can block your calls. Do you know that? If there are too many people trying to send SMSs at the same time, it can block your call because all the control channels are flooded with SMS. If all the control channels are flooded with SMS, somebody who wants to make a call is not able to get a dedicated control channel, right? So sometimes that can happen. In fact, I think people have done studies on what is the upper bound on the number of SMSs that can flow and so on. SGSN is the MSC. Okay, just think of the SGSN as a packet enabled MSC. So everything that the MSC does, the SGSN also has to do. MSC knows only how to handle voice, that's all. See, I just take the MSC, I add one more small box beside it which knows how to handle packets. I put both of these things in a bigger box, I call it SGSN. Right? That's it. Because MSC, the protocols that the MSC knows are meant for handling voice. Right? The MSC, for example, does not know that I should contact another GSM and ask for a temporary IP address. That's all. See, you don't want to deal with too many different entities in your system, right? So, GPRS is not only for data. GPRS is meant for carrying voice as well as data. Okay. So, when I am doing a voice call, my SGSN will behave exactly like an MSC. Okay. When I am doing a data, that is when the SGSN will not behave like a normal MSC, but it will do the additional functionality of trying to check is there an IP address, get the IP address, route the data packet. So it's just for convenience that you put both the boxes into one box. Okay, so the question is there any limit on the number of IP addresses, temporary IP addresses that the GSM can assign? So it is similar to what an ISP does. Okay, so that is why there is this notion of PDP context. So the IP address is not assigned to you for life. It's assigned to you for a certain duration of time. So the PDP context will say that you have this IP address for so much amount of time, right? So after a certain amount of time, so the GPRS node, so I had actually intended to skip all these things. So the GPRS handset has 3 modes of operation, okay? One is the idle mode, one is the ready mode, and one is the active mode, okay? So when it is in the idle state, it doesn't have any PDP context associated with it at all, right? So it doesn't have any IP address, nothing. So once an IP address is assigned and let's say it does a data transfer, so it becomes active, okay, and then it goes back into what is called the standby mode. So when it is in the standby mode, it doesn't, again the PDP context becomes deactivated. Okay. So that IP address becomes available for other nodes. When this node again starts another transfer, it may get a different IP address. It's just like at home, when you switch on your machine and connect to your ISP, you will get one IP address. When you switch it off and switch it on again, you need not get the same IP address again, you may get a different IP address. So the same mechanism holds, except that you don't have to switch off the GPRS handset. Even if the handset is on, but there is no data transfer that is ongoing, this mechanism can happen. Okay? Let's take a 1 minute break. Okay? Okay.